Good morning, everyone.
Morning.
Good morning. So if you are able to open your camera and say good morning to your classmates, please do it.
Morning.
Good morning.
Good morning.
Good morning.
Good morning.
Okay, they haven't solved the problem yet in our classroom, so we have to continue online. So let's see when we are going to they are going to solve the issue in our classroom. And if I hope they can change the room, because I have another section they changed the room, but for this one they haven't changed the room yet. They haven't assigned a new one yet. So let's work online. Okay, do you have any questions? Any questions? Okay, so today I'm planning to go over the code for chapter 2. So we practice on R, and then we will practice on some real data set. So let's practice on R. So let's open the Canvas page. Let me share it first. Open the Canvas page, and then click on Files, and then download some files. Let's download in the data. For data, download some data we're gonna practice on. Click on data. And download this row time experiment. I will explain this one and practice on it. So please download this one. This is the first file we need to download. And then go to File again. Go to Files. I'm going to release the homework today after class. Directly after class, I will release homework number 2. And then click on R code and material. And then click on chapter 2, R code. And then download this one. So far we have downloaded 2 files. The first one is the data, and the second one is the chapter 2 simple comparative experiment R file. We're gonna practice on this R file and then practice on some real data set. Okay. So let me open the R file. After you download the R file, please double click on the R file, which is the chapter 2 simple comparative experiment. Click on this one to open it. When you click on this one, it will open the R file. All the code that I have used in chapter 2. So practice on this one. Let's do it again together. And I will go over this code again. I know I went over this one during the class, but let's do it again. And then I will ask you to practice on some real data set. So please focus, because I'm going to ask you to practice on some real data sets on your own. Okay, so you see my screen, guys? Do you see this file? No one reply. Please, do you see my screen? You see chapter 2 simple comparative experiment?
Yes. Oh, it's still on Canvas. If that's
It's
what
still
you're
in Canvas?
Yeah.
Okay, thank you for letting me know. So you see this file, the program for simple comparative experiment chapter 2?
Yes.
Okay, very good. So now let's practice on this one. In our lecture note, chapter 2, we covered 2 applications. The first application was comparing 2 fertilizers in terms of yield. We called them fertilizer A, fertilizer B. And this one was in chapter 2, part 1. In chapter 2, part 2, we practiced on another data set or another application, which is the 2 taps. We need to know which one is better in terms of hardness. So tap 1 and tap 2. So in these 2 examples or these 2 applications, we can compare 2 treatments, and we need to know which one is better than the other. The first part, or part 1 in lecture note of chapter 2, we practice on 2 independent samples, because the plant is assigned to fertilizer A is different from the plant is assigned to fertilizer B. But for the second example, the dependent samples, these two taps randomly assigned to each specimen. So each specimen will be divided into 2 parts. One part will be assigned to one of the taps, the other part will assign to the other tap. So it is paired case. So let's practice on the first one again, with the tomato example. The yield for fertilizer A was 5 values, and the yield for the fertilizer B was 6 values. So I created an object, or I stored the first data set under yield A. I stored the second data set under yield B. So let's run these 2. When I run this one, you see at the right-hand side, it said you stored yield A, and in this vector you have 5 values, and this is the beginning of these values: 29.2, 11.4, 25.3 to the last one. Let's run the second line. It said, oh, you saved 6 values again under fertilizer B or yield B. Now I have 2 vectors of values. I can work with these 2 vectors of values. The first thing I need to do is, let's have another column, because I need to do my data as the first column is fertilizer A, fertilizer A, fertilizer A, fertilizer A 5 times, and then fertilizer B, fertilizer B, fertilizer B 6 times, and the second column is the data itself. So I used and I put them in a data frame. So in a data frame, I created a column called group, or you can call it fertilizer. It's up to you. And then you repeat fertilizer A 5 times, repeat fertilizer B 6 times. So when you run this code, you get this one will make a column, has fertilizer A repeated 5 times, fertilizer B repeated 6 times. And then I'll create another column. I called it weight, but you can call it yield. It's up to you. And I saved in this column yield A data and yield B data. And I stored in a data frame, and then close the brackets. So let's run this one. And then let's print the data. You can write down print the data, or just print my data, or you just write my data. So when I look at this data, see, I created this column using this code. Repeat fertilizer A 5 times, repeat fertilizer B 6 times. Use this column, and I called it group. The second column, I added the first 5 values and the 6 values in one column. So now I have 2 columns. I would like to calculate the mean of the first group, standard deviation of first group, variance of first group, and how many values in the first group. Do the same thing for the second one, and also the minimum and maximum. I know you can see the values, but if this data is very big, you need also to count how many values for first group, how many values for second group. So I use a function called the grouped by. This one function is in this package. So you need to install this package first, and then you write library, the name of the package. To be able to use the function in this package, this function group by, do what? this group by function can be used to run some commands or do some operations or some calculations for different groups. So you write down group by, give the name of the data, and then give the grouping variable. The grouping variable is group. You can call it anything like fertilizer. It's up to you. Those are only names. So he gives the name of the data and then gives the grouping variable. And then using the summarize function.
/founder set * verify.
Excuse me? Any questions? Okay, if you have any question at any time, please unmute yourself and ask me the question. So you can use the summarize function to do many calculations on each group. Like I would like to use the count n of each group, the mean of each group, the var of each group, variance, standard deviation of each group, the minimum of each group, maximum of each group. So these summarize function and group by will apply these functions on each group of data. So let's run this one and see the output. Those are the output. The count, we have 5 values for fertilizer A, 6 values for fertilizer B. The mean for fertilizer A is 20.7. The mean for fertilizer B is 22.5. The variance, standard deviation, minimum, maximum. This is numerical summary. And we looked at this one. I said, oh, looks like fertilizer B is higher than fertilizer A. So let's look at the histogram. This is graphical summary. This code is used to have all the plots in one graph. But I can run only this one. See, let me show you the difference. When I run this one, it gives me a histogram of A. When I run this one, it gives me a histogram of B. But I need both of them in only one plot. You can use the function bar. It's up to you. You can use it or you can have like this one. Bar and give MF rows because I have two graphs. So I can put them in a row. The row has 2 columns. Like if I have 4 graphs, I can make this one 2 by 2. So I should have 2 rows and 2 columns. But because I have only two plots, I can make them in a column or I can make them in a row. So I used to make them, I like to have them in a row. So run this one, run the first one, run second one. You see the difference? This one only one graph or only one plot. But it's up to you. You can run only this one, run only this one separately. It's up to you. But I like to do this one. And then let's look at the box plot. The function box plot can be used to graph the side by side box plot. So how do I graph the side by side box plot? You give the response variable first, and then you give the grouping variable, and in between you should have tilde symbol, this one. So the first variable is weight, which is in the data, my data. And the second variable, which is the grouping variable, is called the group in my data. And then I can write only this one inside the brackets, but I can add some X label and Y label. You can remove this one, it's up to you. But having a title and having an X lab label, Y lab is something good. So let's run this one. You get the side-by-side box plot. Oh, looks like it's still this one is active. If you'd like to remove this one, it's fine. Remove everything is fine, and then run this one. This is the side-by-side box plot. It looks like the fertilizer B is higher than fertilizer A based on the median, because the median of this one is higher than this one. But I know the fertilizer A, fertilizer B looks like different, but we need to know this difference is significant or not, so you need to do a test. But we cover 2 cases. One of them is assuming sigma 1 square equals sigma 2 square. The other one is assuming sigma 1 square doesn't equal sigma 2 square. So you use the same function t-test, and you give the first group of data, second group of data, but the option variance equal, can be true, can be false. It's up to you. But which one I should use, I will let you know. Based on the rule of thumb, you divide the big standard deviation by the small standard deviation. 7.03 divided by 5.43. If the ratio is greater than 2, you assume unequal variances. So equal variances is false. But if you divide the big by the smaller one and the ratio is less than 2, you use the variance equal true. You assume sigma 1 square equal sigma 2 square. For our case, ratio is less than 2. So we should go with the equal variances based on the ratio. But there is a test. I will show you the test that we see these two variances are standard deviations are equal or not, which is equivalent to variances are equal or not. So let's run this one based on the rule of thumb. You look at the p-value is big, so you fail to reject H0, which means the two fertilizers are the same at significance level 5%. Even if you used 1%, you still fail to reject. If you assumed unequal variances, the output, the conclusion is the same. The p-value is big, so you fail to reject H0. But again, which one I should use? Equal variances or unequal variances, because sometimes they give you different results based on the rule of thumb, or which is something better, based on a test for equal variances. The function is var.test. You give the first group of data, second group of data, and then ask or to run the var test. Run the var test. And var test, the null hypothesis is what? Is equal variances. The alternative hypothesis, unequal variances. So let's see the variances are equal or not equal based on the test. P-value is big, so you fail to reject H0. It means the variances are equal. Sigma 1 square equals sigma 2 square. And also it is the same thing. A rule of thumb said the same thing. Okay, checking the assumptions. Because before we make the conclusions, like the two yields are the same, because p-value is big, I need to check the assumptions, because the assumptions are very, very important. If the assumptions are satisfied, my conclusion is correct. But if the assumptions, one of them is not satisfied, you need to fix the problem. And I will show you later how to fix the problems. So now let's use some graph for the normality. That graph is called the QQ plot or QQ norm. And R is called the QQ norm. And I think in many tabs it's called the Q normal probability plot. They are different names, but in R it is QQ norm function that you use to get the QQ plot. Anyway, you can graph this one separately. Looks like straight line. The dots are making a straight line. Looks normality is satisfied. The second one, normality looks satisfied. I know this one is far away a little bit from the straight line. This one is far away a little bit of the straight line. So it's better to look at the test, Shapiro test. And if you'd like to put both of them in only one graph, you can run this one, this one, this one. And if, let's do the test. Let's see normality is satisfied or not. When you run the first one, p-value is big, so you fail to reject H0. It means normality is satisfied for the first group. Also, the second group should be normally distributed. P-value also is big, so normality is satisfied for the two groups. So my assumptions are satisfied, so my conclusion is correct at 5% significance level, which is the two fertilizers are the same in terms of yield. This is for lecture note number 1. Do you have any question, guys? Any question so far? Okay, so let's cover the second application, which is two dependent samples. We had two tips, and we need to know which one is harder in terms of the which one is good in terms of hardness. I saved the first group of data under tab 1. I saved the second group of data under tab 2. And then I use the t-test function again. It is the same function. But the difference is what? The difference is paired equal true. Because the default is paired equal false, it means the two samples you gave me are independent. But if you'd like to let R know that they are dependent, you need to use this one, paired equal true. And the alternative is doesn't equal, but actually this is the default. If I remove this one, is no problem at all. But I change this one if the alternative is doesn't equal. The alternative is greater than or less than or doesn't equal. So if the alternative is greater than, I change this one to be greater than. If the alternative is less than, I change this one to be less than. But if it doesn't equal, I don't need to write this one because this is the default. So let's run the test. The p-value is very big, so it means the two tips are the same in terms of hardness. But keep in your mind, there are some assumptions. We need to check the assumptions first before you make any conclusion. I know p-value is big, but I shouldn't look at p-value before I look at the assumptions. Keep in your mind, the assumptions are not on the two groups. The assumptions about the differences follows normal distribution. So in the first case, we checked the normality for each group, but for the dependent case, you would check the normality for the difference. So let's calculate the difference first, step 1 minus step 2. And let's graph the histogram of the difference. But as I told you that the histogram doesn't work if the sample size is small. And the sample is very small, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's only 10. So what should I do to check normality? You use the QQ norm, and if you do not feel confident, you use Shapiro test. So let's look at the box plot also, because the box plot can show the symmetry. Looks like the data is symmetric, normality is satisfied, but let's do something better. Let's do the QQ norm and add the QQ line. Looks like normality is satisfied, but I'm not sure because there are many values far away from the straight line. So we need to check the normality using some kind of test. But there are many tests. One of them is Shapiro test. This is a very famous one. Oh, the p-value is less than 5%. So it means the assumption is not satisfied. So before you conclude the two tips are the same in terms of hardness, you need to fix this problem. You need to fix normality. How do I fix normality? I will let you know later how to fix normality. You can use some transformation. I will let you know how to select the transformation. Or if everything failed, you are not able to fix it at all, you need to go to the non-parametric tests. But the problem with the non-parametric tests is that they have less power compared to the parametric tests, like t-test. T-test is much better in terms of power. So if you can fix the problem or you fix the normality, will be great. Any questions so far, guys? Any questions so far? Okay, let me talk about some real data sets. Let me first open some little presentation. You see my screen, guys?
Yes.
Yes.
Guys, do you see my screen? A real experiment?
Yes.
Yes.
Okay, that's good. So let me talk about this real experiment. I have just done it yesterday. Let me talk about it. 1 second, I will stop my computer. Okay, let me talk about this real experiment I have just done yesterday. It took something like 1 hour and a half. It took for me 1 hour and a half. Which pass takes less time? Okay, let me explain the experiment I have done yesterday. I came to the United States as a collegiate assistant professor in 2018. And I was before a graduate student, but I went to Egypt for 2 years, and then I came back after as a collegiate assistant professor. When I came to the United States in 2018, one of my friends was living in Fox Ridge in this building. My pen doesn't work. 1 second, please. Always my computer do this. It's get freezed from time to time. Let me. Sorry, guys, but sometimes my computer is not nice. So, one of my friends was living in Fox Ridge in this building. Okay, you see my screen again? Guys, you see my
Yes,
screen?
we can see it now.
Okay, thank you. So I noticed that he is all the time taking this path to go to the Bryce's Fork, to go to campus or any other place. He takes this path all the time by his car. To go to Fox Ridge. To go to the campus. All the time. So when I asked why you are taking this one, because there is another nice one, which is this one. You go this way and then you go Duck Pond, this one, and then you go to Bryce's Fork. Why this one is shorter, but he said the one I use, it has only one yield. There is a yield in this one. There is no signal at this point. This is the only thing I see. And there is a signal light at this point. But he said, if I use the other one, this one, if I use this one to go to Bryce's Fork, it is shorter, but there is a stop sign at this point, and then there is another stop sign at this point, and there is a signal at this point. So which one on average? Because I feel like maybe this comes something like psychological feeling, like because there is no stop sign, there is no much stop sign, and there is no is only, but this one is only one signal, there is only one signal, but the difference is what? There is one yield, but here there are two stop signs. Maybe people doesn't like stop sign. So I have this research question since I talked with him, that which one on average take less time? Maybe they are the same, but the one he is using, it is longer, but maybe it take more time. I don't know. So I decided yesterday to see which one is longer or which one is shorter. It take less time. So I did the experiment 6 times for each. So in this case, we have 2 treatments. Let's say this pass is D, dog bone, because you pass this one. Let's say the other one is F, because you pass the food line. So we have 2 treatments, D and F. And I used a coin. If the coin is face, I use the dog bond pass. I go from this way, and I count the time from this point up to I reach this point. And if the coin is tail, I go from the food line pass. I did the experiment 6 times for dog bone, and did the experiment 6 times for food line, using a coin randomly assign which one I use. And then I collected the data, and now we need to practice to see the 2 passes are the same or the 2 passes are different in terms of time. And let's see and then discuss this problem. So we downloaded some data set. It's called road time experiment. So I will give you some time to modify the code and practice on it, and let me know the 2 roads are equal or they are different in terms of time. We have H0, mu1 or mu-f equal mu-d against HA or H1. Let's test the assumption of my friend, or the claim of my friend, that mu-f, like the food line, is less than mu-d, or you can write it down, mu-d is greater than mu-f. It's up to you. So let me show you the data set. The data set downloaded. Let's go to the data. You can download. Let me share it. This is the data set I asked you to download at the beginning of the class today. This is the pass, F is food line, D is dog bone, and those are the time. 6 for F and 6 for D. So please use the code that I have just practiced on, modify it, and practice on this one to see F equal D, or F is less than D, or D greater than F. Okay, so the only thing you need to do again is use this code, use this one, modify this one, but do not use the paired theta's, because these are 2 independent sample case. So you need to practice on this part. Modify the code, and please let me know the two routes are different or they are the same? Go ahead, take your time. And let me know if you have any question. But by the way, let me talk about some point I forgot to talk about. This problem, this real experiment, has many confounding variables, has many possible confounding variables. Do you know these confounding variables?
Maybe the speed of your car.
Very
Okay.
good.
Time of day, depending on the traffic.
Very good. Time of day. Very good. What else? I thought about the day, the time of the day, the driver behavior, the driver gender, the speed. Those are confounding variables, and I controlled all of them. How it comes? Because I did the experiment at the same day, at the same time. Yesterday, and I did it at night from 9:20 to 10:30 or 35. So it was almost the same time, the same day, because maybe Sunday is different from Monday, different from Tuesday, and also maybe the time morning is different from evening, different from afternoon. So I controlled these two confounding variables by doing the experiment on the same day, at the same time. And also the driver behavior, maybe people are different from each other. So did the whole experiment is only one person, which is me. The driver gender, let's say you can generalize to the all males, but actually because I controlled the speed also, I maintain the speed to be 30, and on the prices fork to be 40. I try to make it very constant, or it doesn't change at 30 inside Fox Ridge, and on prices fork is 40. So I controlled all the confounding variables actually. So I think it is a good experiment. So please continue practicing. So we need to modify this code. Let's see who will get a good conclusion first. You can import the data into Excel, into R, or you can modify the code, enter the data, like yield A the data, or F equal data, D equal the data. You can enter the data in the within the code itself, or you can import the data from Excel. It's up to you. Do whatever is easy for you. If you get any information, let me know. Like after you get the numerical summary, let me know something, you got something, or the graph is gave you some information or anything. Someone is asking me what you wanna us to do. What I said is that I explained some experiment. I explained this experiment of 2 rows. I don't know why is my writing is not. And I collected data. We collected data, explained this data set. We have 2 treatments, one is F, one is D, and we have the time. And now I ask you to see the mu F and mu D are equal, or mu D is higher than mu F. Because my friend is used to use F, which is a food lion pass, compared to the duck pond pass. So you have some data for 2 treatments, and I'm asking you to modify the R code that we used in chapter 2, part 1. Modify this code to see which, to see the 2 means are equal or they are different in terms of time. So you need to modify this code to practice on that real data set. This code. Guys, please, anyone, is there anyone didn't get what I'm asking for? Does anyone didn't get what I'm asking for? I'm asking you to practice.
I think I got p-value 0.513.
The p-value
0.513.
0.513. So it is
Yes.
greater than 5%.
Yes.
It means the 2 passes are the same.
Yes, I think I did this equal or unequal variance test, and then I got, it says the unequal variance, so I use var.equal equals to false.
Okay, so what is the standard deviation for F? What standard deviation for D? What is the rule of thumb set? The rule of thumb
Standard deviation for D is 12.3 and F is 21.4.
So is one of them is not 2 times the other one. So it means equal
Yes.
variances.
Oh, yes.
So the rule of thumb said equal variances.
Yes.
The test said unequal variances.
Yes.
Okay. So assume if I don't remember this because I have done the experiment yesterday, so I will do it with you in a few minutes, but after you practice, but please don't wait until I do it.
Yes. When I
you-
did this raise.f test, the p-value is 0.246, so which means like it is unequal variance, right? It's greater than 0.5.
Okay.
So
If it is unequal variances, you go with the results with the unequal variances, which is this one.
yes.
Okay.
So I did that. Yeah.
Very good. And go ahead.
Okay. So when I did that, I got my p-value greater than 0.05, which is
So it means the
failed
two
to
passes
reject
take.
null hypothesis.
Very
So,
good.
yeah.
So far, it means the two passes are the same in terms of the time.
Mm-hmm.
But keep in your mind, you haven't continued, because before you make any conclusion, also you need to make sure the normality is satisfied. If normality is satisfied, your conclusion is fine. Now it means the two roads take the same time. And my friend prefer the food line pass because of some kind of psychological effect. Like, looks like this one, I don't want to stop too many. So it's nice road, so I take it all the time. But you need to
Is
make
it like
sure
we have to test normality as well?
Yeah, sure. Because before you make any conclusions, because this test, the t-test, under normality assumption. So you need to make sure the normality for the t-test is satisfied. Although actually there are some papers published on the internet, they said the t-test is robust for normality. It means if the normality, I know normality is very important assumption for the t-test, but even if it is not satisfied, the t-test give good results. But anyway, let's test the normality assumption.
Okay, let me do this.
So let me do it with you. You did a good job. So the only thing you need to do is normality. So let me do it with you. So now I will make the first one as F. Let's say the first one is F, which is food line pass. Second one is D, dog pond pass or road. So let's have the 6 values for F, the food line. The first one is 124 seconds. I forgot to say these data with seconds. 124 seconds, 36. The second try is 175.28. Third try was, if I did any mistake, please let me know. 140.15. And this try number 4 is 126.5. And then 119 second, 0.48. Last one is 119 second, 0.89. And the second group of data for dog-bound pass or road, 130.24. Second one is 145 second, 0.49. Third one is 128.79. And 134. If I did any mistake, please let me know. 35. 1, 2, 3, 4. 1, 2, 3, 4. And then 160. Second. 0.52. The last one took 147.7. Those are the two groups of data. Now I would like to have my data frame group. Fertilizer A is food line. The first one is food lion pass. Second one is backbone path. And the first one is repeated 6 times. Second one repeated 6 times. And then yield A is F data, yield B is backbone data. So let's see the results. See on average. Let's run this one again. Second one. My data. This is my data set. Food line 6 times, backbone 6 times, and the weight. Oh, let me change the weight to be time. Let's make it much better. And the group is path. Let's see, more nice. So this the path is food line path and backbone path and the time. Now let's have the numerical summary. The my data, the group is the path, grouping variable, and the response variable is time. So let's have a copy from time. Paste, 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 paste. Let's look at the numerical summary. Oh, looks like the food line pass take higher time. Is 134. Oh, sorry, less time. The one is my friend is used to go as the food line pass. It will take only 134 second on average. But the backbone take 141 second. And the variance standard deviation. The standard deviation of backbone is 12.3, food line is 21.4. When I divide this one by this one is less than 2. Less than 2 means the rule of thumb, assume sigma 1 square equals sigma 2 square, but the test is much better. But let's look at the histogram of F, histogram of D. And let's put both of them in only one graph. Run. The histogram doesn't give you much information because the sample is very small, so don't care about the histogram. So now let's look at the box plot. It's much better than histogram. Let's use the numerical variable is time. The other one is path. And this one is path. And this one is time. Then hit. And let's have an only one. Yes. Oh, looks like the food line, the backbone, take higher time based on the median. Median is higher than median of the food line. So far, everything shows that we have only, it looks like the backbone is better. But let's do a test. Based on rule of thumb, we should use equal variances. Should use this one. This one. Equal variances is true. So run this one. The p-value is very big. It means they are equal in terms of average time. But let's make sure this one, the one we should go with by doing the variance test. Yeah, equal variance test. So make sure equal variance. Oh, this one I haven't finished. Change this one. Guys, if I do any mistake, let me know. The first group is F. Second group is D. So p-value is 0.5094. Still, p-value is big. It means f and d, mu f and mu d are equal. They are not different. I'm not going to modify this one because I'm going to go with this one, equal variance based on rule of thumb. But let's do a test. Equal variances. F, D. To make sure equal variances is satisfied. The p-value is big. So like the rule of thumb, I can assume sigma 1 square equals sigma 2 square. So I don't need this one. But I need to check normality. I need to check normality because one of the assumptions for equal variance for the t-test is normality. So let's do the normal probability plot or QQ plot for F and QQ plot for D. And put them in only one graph. Run, run, run. Oh, looks like this one is normality, looks like satisfied, but this one looks like we have some value very far away from the majority. This is the one which 175.28 for food line. So I would like to make sure normality is satisfied. So you need to do a test. It's better than graph. This one is F. This one is D. Shapiro test. Oh, normality is not satisfied for the first group. Normality is satisfied for the second group. Okay, guys, now we need to discuss this case. What should I do? If this is your study, what you should do? Go ahead, let me know if this is your study, what you should do, because the assumption for normality is not satisfied.
Maybe transforming the data.
Very good. This is one of the solutions. Transform the data. I will try to find some transformation for the data, like the square root of the data, the logarithm of the data, squared values of the data, and so on. This is one of the solutions. I will cover this one later, and I will let you know how to find the appropriate transformation that make the normality satisfied for your data. What else?
Maybe increasing the sample size.
Very good. Another good solution that you can increase the sample size. Maybe 6 is not enough because maybe 6 is a small value or big value. How did you decide that I'm going to do the test or I'm going to run the experiment under each treatment only 6 times? So I decided this one because of the time. I have only 1 hour and 30 minutes. So I said I'm going to do the experiment by my car for 1 hour and 30 minutes. So I did 6 for the treatment F and 6 for treatment D. But later I'm going to cover something called power of the test, the power analysis. Based on the power analysis, you decide, the formula actually decide what is the sample size that is enough for your experiment. So I'm going to cover something called power analysis to make sure 6 for each treatment is enough or not. What else?
Go with a non-parametric test.
Very good. Another solution where someone is who looks like normality is not satisfied, I will not use a transformation. I will go to non-parametric tests because non-parametric tests are good choice if the sample size is small. What else? Maybe someone says, oh, the t-test is robust to normality. It means if normality is not satisfied, still t-test give good results. But if this is my study, actually, I will go and find some transformation first. I will do my best to find some transformations that make normality satisfied. And then if I couldn't, I will increase the sample size. If I couldn't increase the sample size, I will go to non-parametric tests. Okay, but the last one is fine, but it's which is the normality. T-test is robust for normality. There are many papers published on that. T-test is robust for normality. It means even if the normality assumption is not satisfied, it still give us good results, but I'm very worried about this value, which looks like outlier value. When we looked at the box plot, see, it is outlier value. This one is outlier. The 175.28 for food line. Maybe this one is the reason why the food line take, which one take more time? The food line or which one take more time? The duck bone take more time, although this value is a value for the food line. So even if this value is big, still the duck bone take much time, which means looks like we need to increase the sample size or find some transformation to make sure they are different. Okay, guys, any questions so far? Do you have any questions? Okay, I'm done for today. This is what I'm planning to cover. If you have any question, please let me know.
Thank you. Have a good day.
Thank you. Have a good day.
Thank you.
Thank you. Thank you.
Thank you.
Thank you.
Thank you.
Thank you. Have a good day. Thank you, guys. Have a good day. See you.